Hello, everyone. It's very exciting to be here to present my group activity on turbulence modeling. My primary research area is turbulent flow. So I have a great interest in developing turbulence models. Here, I'd like to present a modeling approach with a machine learning technique for separated turbulent flows. Before I start, I'd like to acknowledge my outstanding students. They are also the co-authors in this talk. They accomplished a very interesting piece of work this year, which I'm going to present today.
So these are kind of general contents. And as you all know that we can either choose or there are kind of two categories in turbulent flow simulations. One is RANS. Professor Heng Xiao gave a nice talk on what these are, what this is. And the second category is eddy resolving simulation that includes LES, DNS, any other high resolution, high fidelity technique. So if you look at the simple flow over a flat plate, RANS simulation gives us very simple, smooth profile flow field because we are looking at the mean flow. However, turbulent flow has lots of fluctuations, right? And the RANS give us the result in a very short turnaround time. So it's very fast. For this type of calculation, it probably takes a few minutes or a few 10 minutes. However, the LES calculation, even for simple turbulent boundary layer flow without any separation, we probably need to spend 1 day or at least a few days, right? And however, the modeling error in the RANS is quite high. It's probably okay for attached boundary layer, but it's well known that it's not so accurate for a separated flow. So that's what we are looking at. So RANS simulation is widely used in industrial application because it's short turnaround time, but it is limited in predicting a separated flow. And one simple example is coming from the airfoil case. So when we conduct RANS simulation on the airfoil, we often get higher lift beyond the store angle, where when the airfoil experience significant flow separation on the suction side. And this is related to the delayed flow separation in the lens computation and compared to the reality. And so here the experimental data shows the lift versus angle of attack, and Sparrow's Almaraz, a popular RANS turbulence model data is shown here. Then, so we like to use this machine learning or artificial intelligence or data-driven techniques to improve the RANS model. And our target is for the separated flow because it is one of the well-known area where the typical RANS model, the conventional RANS model, is often fails. And our group touch upon three approaches. The first one is field inversion and machine learning. The previous speaker gave us nice overview on this topic as well. The second one is the Reynolds stress model. There we like to avoid boostiness approximation and try to get a better representation of the Reynolds stress with mean flow variables. The third one is Bayesian optimization. There we can optimize model coefficients, turbulence model coefficients. Here I have an example for K omega SST. There are like 15 model coefficients, and we can have a better way, optimized way to calibrate this model coefficient for certain flow problems. Today's, due to the time limit, I like to focus on the field inversion and machine learning that we use as a tool to apply this method to separated flows. So in this field inversion machine learning technique framework, there we can optimize mathematical formulation of the model equation. And we start with, so for example, we can start with the given Sparrow's Almaraz equations here. On the right-hand side, we have the production term, destruction term, and viscous diffusion term. We have a good representation of the balance between the production and destruction term in order to get the better value of the eddy viscosity that goes into the RANS equation, the governing equations for the flow. And we can optimize this data, to satisfy a cost function, and I'm going to show you the cost function a few minutes later, and then we can get this data distribution in the space. And we can use the machine learning technique to get the relationship between the flow feature eta is some example of eta is flow features are given bottom. You can get the relationship between eta to this data, the correction term for a given turbulence model. And by the way, this method is suggested by Kartik Grasami's group at University of Michigan about 4 or 5 years ago, and we're kind of learning this method at the beginning of this year, and then we are applying this method to separate flow. So, in a one simple slide, I can overview. I can give you a general view on this field inversion machine learning technique that is applied to a particular machine turbulence model. So, as I said earlier, there's the first step is field inversion. In this step, we can optimize a turbulence model through a parameter beta. So again, I have this example, Spart-Armor's RANS model, a popular RANS model nowadays. And so we modify the production, but this modification actually is doing the rebalancing between the production and destruction of the viscosity. And we're using the machine learning technique to get the relationship between this correction term data with the flow features. And those flow features are that we are using 4 flow features, and these are suggested by the Kartik Grasami group from the Michigan as well. And the first term is the ratio between production to the destruction term. And the second is the strain rate magnitude with respect and then scaled by the rotation rate tensor magnitude. And the third one is more like eddy viscosity scaled by the molecular viscosity. And the last one is the shear stress inside the boundary layer with scaled by wall stress at the wall. So then from the machine learning technique, we got the beta. This as a function of theta. Then for the new test case, we simply run an original RANS model in the RANS simulations, then obtain this flow feature eta. Then using this machine learned, the neural network part, we get this data from the machine learned part. Then we use this data in the new turbulence model, the new optimized model, then use this model in the RANS calculation to get a better RANS results. So here I have 2 examples. One is simple airfoil case, and the other one is axis symmetric based flow. And airfoil case is quite kind of standard kind of tutorial case that was also used by Kartik Grasami group from the University of Michigan. And this airfoil is S809 airfoil. And this looks like this. It's quite a thick airfoil. And it has separations on the, even in the small angle, like a 10 degrees. And this is the equation that I repeatedly show. This is SA RANS equation with the beta, the correction term on the production, in front of the production term. And the cost function in this case, so since we know that conventional RANS model, this baseline RANS model, SA RANS model, give us over prediction of the lift beyond the store angle, we like to get a better prediction of the lift, aerodynamic lift. So we put this cost lift in the cost functions, and this optimization problem could be numerically ill-posed. So we put this regularization in the second term. And so basically the training data is simply the field inversion data so that we have this data distribution in the space. And we also have this flow features distribution in the space as well from the the initial SA RANS calculation. And we picked these 3 angles, 12, 14, and 18 degrees for the training data set. And then we tested at different angle of attack. 4, 8, 9 are small angles before the stall, and 16 and 20 degrees are beyond the stall angle. So we have a good prediction. This red one shows the field inversion machine learned data, and that's very close to the experimental measurement. And the other second nice result is that in the pre-stall region, we should have almost the same result to the baseline assay, and that's what we have. So that's quite nice. And here I have a pressure profile of that airfoil that we saw in the previous slides. So I have a 4 angle of attack, 4, 8, 16, and around 20 degrees. So for the small angle of attacks, pressure profile is the trained assay model is more or less same to the original assay model, which it should be. And for high angle of attack beyond the stall angle, the trained assay model results show the better agreement to the experimental data. I emphasize specific region where the flow becomes separate when this pressure profile is more or less flat on the suction side. And on the right-hand side, even though we put a lift in our cost function, since we have a better good estimation of the pressure profile on the airfoil, the moment prediction, so these values are there than in pitching moment, and so then this method gave us a good representation of the pitching moment closer to the experimental data. The experimental data shown the symbol blue line is trained assay model results. Black one is baseline assay result model. Then after we have done this kind of validation effort, so we like to learn this FIML field inversion machine learning technique in this kind of tutorial case. Then we like to apply a new different geometry. So this is axisymmetric based flow that we are interested in at this moment. And here, this is kind of schematic diagram. Because of the blunt trailing edge or blunt base geometry, we have very massive separations. And after that, we have this recirculation region. And as the Mach number increase, we will see the expansions and recompression waves in the wake as well. And in this case, predicting the pressure on the base plane is quite challenging. And this is important. Predicting the pressure on the plane, on the base plane is important because it directly leads to the pressure drag on a axisymmetric body. So the rest has a limitation in predicting the separating flow. Particularly, and here we are interested in predicting the base pressure, the pressure on this base plane. And the RANS gave us quite interesting pressure distribution, which is not close to the reality. And high fidelity shows and experimental data shows quite uniform pressure distribution on the base plane. And on the right-hand side is this area average base pressure, and across the wide range of the Mach number, including subsonic, transonic, and supersonic. Symbols are experimental data, and also the one is the pink one is the high fidelity computations. Two lines are typical RANS results. So the blue one is shear stress transport model, SST, K omega SST, and the red one is spiral RANS model result. And across this Mach number, there's no one turbulence model that can predict this flow quite well. So we pick this case, and then we also pick spiral model because that's kind of the worst worst model compared to the SST. So we thought we may able to improve this model more easily compared to SST. And flow condition is given here. Thanks to the zero angle, we are able to, we can use axisymmetric domain to simply run this case. And then we're going through a wide range of Mach numbers, and the corresponding Reynolds number is given here based on the diameter of the base. And we use field inversion and machine learning technique. So we apply this field inversion machine learning technique. Again, this is spiral anomalous equation with the beta correction on the production term. And here, compared to the airfoil case, we modify the cost function because we like to predict the base pressure on the base plane. So we put the pressure on the base plane in our cost function. Experimental data is around -0.1, this pressure coefficient value. And it's more or less uniform in the radial direction. Okay. And the right-hand side on the bottom, you're looking at evolution of the pressure change in, so it changes as the iteration proceeds. So initially it was the baseline spiral anomalous case, and then you can see that the blue line is approaching the target CP. And so we kind of compared optimized spiral anomalous results, field inversion results, and the baseline spiral anomalous at subsonic Mach number. Here on the left, we are looking at the beta. So if the beta is less than 1, if beta is blue, then we have a less production in the spiral anomalous equation that give us smaller eddy viscosity in the optimized calculations. And that leads us to longer shear layer in the mixing plane. And that gives us a longer recirculation bubble. And this long recirculation bubble helps us to get a better prediction of CP, because the previous one is quite short recirculation bubble, which has a quite low pressure on the center that impacts on the lower estimation of the pressure on the base plane. Similar to the story for the supersonic case, I just have add the numerical shielding image. So in the field inverse optimized flow field, we have a long recirculation bubble, and this small curvature in the base that give us a weaker extension wave. All right, there was a field inversion case. Then we using those field inversion data as a training data, and then we use the machine learning to get the connection from the flow features, flow features, to the beta corrections, the correction term beta to the SA equations. And then we pick these two. One is subsonic and the other one is supersonic Mach number, which are not included in the training data. And we see whether these are test case we see the trained SA model. It provides a good prediction on the base pressure compared to the baseline SA model. The baseline SA give us this red line. Symbols are experimental data. The blue line is field inversion, the trained data sets, and the purple arrow indicates this one subsonic and other one supersonic test case, and it gives a good prediction on the CP in those two cases. And if you compare the prediction, the trained SA results compared to the field inversion case, field inversion data is not used in the training data. So this is kind of field inversion case is a case probably the prediction can achieve in the best scenario. So overall, it's good comparison between prediction and the field inversion, including the beta, eddy viscosity, and also the general flow field characteristics. Same story for the supersonic case. This is Mach number 1.4. And overall, even the numerical serial image is quite similar. And since we have this one, so we have two examples. So far we saw the two examples. One is L4 and the other one is axisymmetric base flow. So we like to evaluate a trained turbulence model with a new geometry. So, and we have, so far we have more data set in the base flow, axisymmetric base flow. So we pick this as a training data set. And the target is L4 case. And this L4 is a subsonic flow conditions. So we pick the subsonic axisymmetric data set for the training. So, and then we checked whether this completely new geometry with respect to the training case, we see good results of the training SA RANS model for this L4 case. So here, black lines is experimental data, red symbols are baseline SA non-trained SA model, and the purple one is a trained SA model. So the drift estimation is much improved. And looking at the flow field, we can see that this trained SA model gives us smaller eddy viscosity, particularly on the suction side near the separation point. So before or after, and after the separation point, boundary layer, eddy viscosity inside the boundary layer, it's slightly smaller than the baseline case. And that actually helps us get separation earlier compared to the baseline. And this gives us a good prediction on the lift beyond the store angle. So here we are looking at the flow field at high angle around 18 degrees. And I believe this is a very encouraging result because I've seen very few studies across various different geometries. All right, so this is my final remarks. And so we use a field inversion machine learning technique in order to train a conventional RANS model, and we pick SA model, and then we test it in two geometry, and we also test this trained SA model from one trained geometry to the different test geometry. And the future work will be adding on more geometry in the training data set and test it in a completely different new geometry. With that, I thank you all for listening to my talk, and I'm happy to answer any questions.
So Professor G, I have some questions. So I think your first assessment on, this model could be applied to predict the flows over various geometries, right? Mm-hmm. So I think that is very interesting, but I think there are some bounds on the shape variation, so what is your bet on it?
So if you ask me whether I can simulate, if I get a better prediction on some completely different geometry other than L4, other than this axisymmetric body, my answer is, well, I don't know. I have to do it. Then we'll see. But at least in these two cases, we noticed that the conventional scalar anomalous model gives a little bit probably too much eddy viscosity in the separated flow region. And this optimization technique allows to reduce that too much eddy viscosity in the flow field. And that helps to get the better prediction. That's kind of the similarity between these two flow cases, even though the geometry are completely different. Maybe we are lucky in this case. So we like to explore. This is basically like 1 year less than a year, still not even the year-long the research. It's kind of 10 months, 11 months research activity. So we like to explore this this method for completely different geometry, completely different flow condition as well.
Right.
This is Ray Singlin. May I make a comment?
Yeah, sure, please.
Okay, I actually have one comment and one request, no questions. First, I'd like to comment that both your talk and Professor Xiao's talk is excellent. And it really opened my eyes. In the past, when we do machine learning, we thought we need to rely on high fidelity results like DNS, right? And ability to improve the predicted capability using not much data set. That's really incredible. And it's really exciting and open up a wide, big door for future development. Now the request, since I used to work for an engine company, and the film cooling of the high pressure turbine is always a challenge, right? Now, I'd like to ask both of you to help us think about what type of data would be needed so we can start the training, do the training, right? So this is a request, not really something need to be answered immediately, but I would love to have some feedbacks. And I can toss it back to Pran and Winnie and maybe bend their arm and ask them to collect the data, start collecting the data. Thank you.
That would be nice. That would be a good opportunity to work with the industry team. And
yeah, we started with Julia Lin, right? And at the beginning, we were shooting for high fidelity simulation to facilitate the machine learning. Now this is a much feasible approach in my view.
Okay. Yeah, thank you for the comment and thank you for saying a good opportunity.
One last question, Dr. G. We have 1 minute left, right?
1 minute, okay.
Yeah. So when we are predicting, we saw two different approaches, right? Mm-hmm. So Professor Branson, yeah, he used a orthogonal basis ROM, and then you are using the machine learning, right? So his approach is very interpretable, and this is all black box, right? So how do you see the accuracy predicted by the reduced order model and also machine learning based technique?
Do you ask me my opinion?
Yes.
Well, I'm not a reduced order modeling guy, so
in a conference,
yes, and so I think both approaches are valuable, and also we can combine those two, right? So then we can give a interpretable, explainable machine learned model. So if you ask me whether I'm interested in reduced order model, yes, I am. Yeah.
Yes, that's an excellent answer. Thank you.
All right.